speaking of exponentials, we're going to do some very elementary stuff here about the number E, and I call this a tale of great interest because it applies to situations where the interest is 100%. I hope we don't have to live through a period like that. That's the way it was when I was teaching in Brazil. I had 100% interest for your economy, basically. Now, how good are power series such as this will give you, particularly the Taylor-Maclaurin series, to approximate a function? And what happens if this interest is imaginary? These are called complex exponentials. We need to just do some review of basic, what should be taught in high school, certainly in the first calculus course. You get at least a standard approach. I'd like to show you a couple of interesting things that aren't usually taught about exponentials. And then the rest of this is what good are complex exponentials, or complex functions in general. And so I'd like you to see that the word easy is repeated here quite a number of times. Easy trigonometry. If you're on a qualifying exam and you forget some trigonometric identities, this is the way to get the answers very quickly and without much trouble. Vector analysis in 2 dimensions becomes very easy using this complex variable theory. Also, it lets you see about complex variables properties that are often misunderstood. I've already talked about phase analysis of classical systems. Oscillators, particularly harmonic oscillators, have phasor clocks. So that's something that becomes easier if you understand this stuff clearly. And rotation, dot products, cross products, all of that will be reviewed, but from the point of view of this amazing, what is called one of the golden, shall we say, crown jewels of mathematics, the invention of analytic functions, complex variables. And finally, vector calculus in 2 dimensions, vector derivatives, the idea of source-free field theory, and then field theory that has sources, down here, and the idea of vector fields with potentials, both scalar and vector. That becomes easier if you know just the simple stuff about a complex exponential and its things, functions like that. What does analytic really mean? We'll see that. And I hope we get about this far in the lecture today, or possibly further. But on the right-hand side here are listed the properties that make the subject easy, and you should know about. So I'm going to begin where this whole story really begins, and that is the whole idea of a banker charging you interest to borrow some money, or giving you interest if you put money in the bank. So if you give a bank a principal, P for principal, some amount of money at time equals 0, and some time t later with this so-called simple interest, they would just simply pay you a final principal at time t of your original principal plus the rate of interest times time multiplying that principal. Now, if you make the rate 100%, that is, if you set r equal to 1.0, like Brazil or Israel at the time I'm talking about it, which was just before the 80s is when it really broke, with 100%, you would get $2 at the end of 1 year. Okay. Well, nowadays, and in fact, as the time built from that time, it became fashionable to do compounded interest, which meant that at the half period, you would get a new principal to add to the principal that you had given at time equals 0, so at t equals 1/2 of the period that you're going to keep the money in there. You get to use that principal to help build your interest a little faster. So the idea is that at time t, I would have this principal here, and then I would use the rate for the half period, you see. So this principal right here equal to 1 plus the rate times t over 2 times the original one, and then this is a new principal to start at the halfway point of the year. Okay. So I would get at the first year 3/2, and then I would get 3/2 multiplied that, so I would get 9/4 of my original $1 that I put into this. We're all sort of cheapskate states here. We're all just putting in $1. We don't trust this banker. So we look at it and we say, my gosh, that was pretty good. Too bad I didn't put 100 or 1,000 or so on. I picked up an extra 25 cents here for each dollar instead of $2 like that. So this is what we want to generalize. Trimester. We do it at the third point. Okay, at time equals 3, I do the rate times the elapsed time, which is only 1/3 of the period now that we're talking about. And this first trimester is the name given to that usually. And then the second trimester you do the same, and so on, so that you get here principal at 2/3 multiplied one more time. Actually, I should be starting down the other end to write this, but this is the basic idea. And here, 3 of these factors, 1 plus r over 3 times time. Okay, well that comes out 4/3, 4/3, 4/3. Okay, 64/27. That's $2.37. So again, we pick up a good deal more than we would have gotten with the simple interest, and a little bit more than the this. So the idea is that after you look at this, you might say, oh my gosh, I could really make a lot of money if I could convince the banker to charge the interest infinite. In other words, just do say 1,000 instead of 3 breaks in the thing, or 1,000,000 or something like that. The question is, would I really end up becoming a rich tycoon with a big cigar and a dollar sign and a bow tie that looks like infinity if I did this, you see? So high hopes for this. If the banker advertises he's going to do this. But the problem that you're going to see is it's not the case. And that's what we need to appreciate. This is a very subtle sort of thing. So basically, let's go over what we had. We had $2 for simple interest, then 1 plus r over 2 squared. Well, that's 3/2 squared. That was $2.25. I picked up 12 cents right there on the next go around to make 37. You see, but I'm only getting 7 cents on the quarterly. You see. And then if you do it monthly, let's just go get crazy here and try to do it with 12. Okay, I pick up $2.61. Okay, instead of 44. After doing a lot more than just quarterly, I triple the amount of periods that I have to make 12. Or let's get even crazy. Let's do it weekly. Okay. Well, 61 goes to with all that change, I only pick up an extra 8 cents, and there's some change. And daily, 365 days of a non-leap year, and I'm getting $2.71 and change, millage. And then let's do it hourly. Okay, there's 8,760 hours in a year. So let's go do that. Okay, and you see you don't pick up but maybe a penny, a fraction of a penny, you see. So this is a very funny limit that is making the answer to the infinite interest, which is E dollars. This is the number E. This is a way to think about the number E if you're trying to teach somebody what's so important about it, and they're more interested in money than they are in physics. They might pay attention to it. So this is, I think, a really neat thing. Remember, it's 100% interest starting with $1. Okay, that's how many dollars you have. That's the limit, at least to 4 figures. Okay. Now, let's go ahead and just, use some really large numbers here. Okay. M equal 1,000, 10,000, 100,000, 1,000,000, 10 million, 100 million, and so on, 1 billion times. If I'm going to basically, in every fraction of a second or millisecond, I'm going to recompute your interest and this product here, you see. And you can see how it's approaching. I'm writing here in bold numbers the value that we know of as E. This is 7.1 here is wrong. This 149 is not, correct. I need to go to 10 billion or perhaps 100 billion products. You see, in order to get E to a precision that it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimals. If I want 10 decimal precision, I need to go 100 billion. That is not a nice way to calculate anything. You don't want to have to be doing 100 billion calculations, you say. But nevertheless, that is the progress of this limit, you see. Basically, 10 to the 6 products to get 6 figures, 10 to the 9 products to get 9 figures. Okay? So, interesting mathematics, but not an efficient way to calculate. And the idea is you can improve the computational efficiency by using a binomial theorem to evaluate this thing right here. So we're going to evaluate that rate times time divided by n as a binomial expansion. And you see what I'm getting, of course, are the coefficients of the binomial. It has a factorial, 1 factorial, 2 factorial, 3 factorial in each of the cases. Remember what factorials are. 0 factorial and 1 factorial are equal, both to 1. Then they start to grow very fast. And because they grow very fast, you see, one of the things you can do is say, I'm really only interested for very large n. I can let this n times n minus 1 be n squared, n times n minus 1 minus 2. I can let that be n cubed. As soon as I do that, you get the power series for an exponential for any interest rate in any time. And the question is, how good are those power series? We need to see that. But that's an exact mathematical expression in any case, which can be carried to arbitrary accuracy across time.
I have a question. So, do we define exponential series as that way, as like a binomial expansion where the first term is 1, like 1 plus x the whole power n? So, is that a definition? Is that how we define exponential e to the x?
This right here is the definition.
Okay.
Yeah, that's right. Good question. And it's fortunate because to get, say, 8 or 9 figure accuracy here, I only have to do a very small number of calculations. The question is, how close do I get for order 2, order 3, order 4, order 5 of the series, you see. Much better than this, where I have to go to order multiplications of billions of times, here I only have to do this much arithmetic to already get 4-figure precision, you see. So about 12 sum quotients for 6-figure precision. That's a lot better than what it took to get 6-figure precision here. It took a million compared to roughly 12. Okay, big improvement, right? That should be appreciated, just as an arithmetic fact. But now we're going to take this wonderful series that's helping us do calculations and really test it geometrically. See what it does with the functions that we know and love, such as the exponential or sine and cosine. So let's just say that we can treat a function of position. This is a mechanics class after all, so that's what we're often asked to be our bottom line in any sort of calculation. Imagine that I do have a power series with these coefficients, and that I'm approximating some function that I know from some other means, such as a solution to a differential equation of motion. And go ahead and say, well, if I have that, I certainly should be in line to calculate the change of the position with respect to time. That is what we call the velocity. Okay, so I go ahead and I differentiate that thing. It's a power law, very easy to write down each of the derivatives of these monomials that make this power law polynomial. And at setting t equal to 0, in this particular case, setting t equal to 0, what I'm going to lose are all of the parts of the power series that have the t in it, and just get that. So this gives us that first coefficient, and this is something we know in sophomore physics, is the velocity at the initial time t equals 0. And then the change in velocity with respect to time, that's what we call acceleration. Same deal. I take a derivative of this thing and get here, for example, with the c5, I get 4 times 5 t cubed, and so forth in that series. And set t equal to 0 now, you lose everything beyond here. Okay, so that you get that the coefficient c2 right here is just 1/2 of our initial acceleration. T equals 0 in place there. And then remember this, we did this where I talked about the NASA terminology for the change of acceleration, A of t, that's jerk. And we do the same stunt once again. We say the jerk is the derivative of this and get a series that involves, with time equal to 0, only that part right there. So 1 over 2 times 3, that's 3 factorial. We'll see that that's not just a trick, but that's indeed what you can get in Taylor series or Maclaurin series, which is what we're doing here. Change and jerk, we've already told that joke. Be silly like NASA is what is going on here. Okay? And the inauguration as change of jerk. Everybody is treating right now Obama as a jerk, and the people that are doing that, I think, are the jerks. But anyway, from here on out is 0, and we just left with this, which is 4 factorial times the initial inauguration. That's the coefficient that will go in place there. And you can go ahead and make more names like revolution for the next one and so forth, but let's just call it a day here. This is a really amazing series when you think about it, because what it's saying is that if the position that you're so interested in mechanics is in fact a function of a time that can be written as a series, then you can say that at an initial time I have here something that involves x of 0, but then at a later time it involves a v of 0 times time, and still later I've got to worry about this one, and so on. At any one time, you see, everything is being predicted to the future just by knowing these numbers.
So Dr. Harter, in elementary mechanics textbooks, the kinematic equation of motion is written as x of t equals x of 0 plus v of t times t plus half a of 0 t squared. Does that mean that it's just an approximation? Like,
it's an approximation assuming that there isn't ever any of these, right? This is the constant acceleration. If I leave that as a constant, let that not be a function of time at all,
okay.
so I just write a here, right? Then I put v of 0. You got to, mention the velocity is going to be a function of time, right?
Right.
With constant acceleration. So is position. That's what you're actually after,
Yeah.
right? So this is your good old university physics #1 formula, right? With just erase that 0 right there, and that's what you guys are struggling to make your students learn if you're teaching UP, right? Okay?
So in that case, v of 0 becomes the initial velocity and a is a constant. So
Yeah. But then let's suppose we have, and there are problems like this, they're usually geometrical ones, but let's suppose it's a problem with constant jerk, right? So I just call this J, that's a constant, right? Then all of these have to keep their zeros because they're going to be variable.
right.
You see, that's the next step. And it's exact if that's really constant, because if that's really constant, all the future ones, all the past are 0, right? So, this is a story I think should be taught to the sophomores that are learning, so that they can see it's part of a bigger phenomena, mathematical phenomena, okay? But it's kind of, it's also a psychological sort of thing if you want to make it home. Just think of yourself in bed, it's time to get up, but you're tired, right? Our alarm clock's already run twice, and you do, oh God, I don't want to get up. So you say to yourself, okay, what's the equation of motion for my getting up, right? And you can say, okay, I'm not going to get up now, but I'm going to get up next. I'm going to get my inauguration up, and then I'm going to get my jerk up, and then I'm going to get my I'm actually going to accelerate out of the bed, and then I'm going to achieve some velocity, and then I'm actually going to get positioned to go have breakfast, right? So, every time you're thinking about doing something, you can imagine that each of these things are starting to light up, working their way up finally until you get that one. Okay, so this is, what's involved in all of our analysis, it's called analysis in mathematics, of functional behaviors. And of course, this fellow right here is really amazing, because every one of those things, every one of those funny things, jerk, inauguration, revolution, whatever you call it, down through acceleration, velocity, and position, every one of them is 1 for an exponential t, right? And then you just replace it with the r squared, r cubed, r fourth power, and so forth. So e to the rt is simply this series with every t replaced by rt. Okay? So the exponential, if you're going to get out of bed exponentially, you see, there can be this long time when it doesn't look like you're doing anything, right? Then, boom, you're out and off, right? So the exponential is really quite amazing. Now, how good is the power series? If we have somehow like a computer that lets us calculate the exact exponential, presumably, here it is going up here, you see, and here it has, first of all, an initial value. If we're using this as our starting point, initial value of the exponential is 1, okay? And then There's a tangent to that right here. That's the first coefficient. 1 plus t is going there, and that's good up to about there. Okay, and then it starts to fall behind what the answer should be. All right, and then the next stop after that is t squared. That's a parabola, quadratic term. There is the parabola that meets the exponential, you see, and it's good all the way up to within a pixel about there. Then the parabola falls by the wayside, you see. Then the cubic, it's good up to about there. Then it falls down, you see, and so forth. The quartic, the fourth term, you see, it makes it to within a pixel to about there. Then it falls away. Now it doesn't look like it's falling away very fast, and indeed it is. But remember, we're measuring things vertically here, you see, so it really is falling a lot more than it looks like. We need another function to study the power series to really get a feeling for what the peel-off of the polynomial terms is. This is a picture in black and white that shows perhaps a little bit better, but still we need better than that to really see the magic that a power series is. A magic or devilishness of a power series is something that you should see. And here's a way to see it, I think, for the cosine. Now the cosine, you see, is an even function, so it only has even polynomial terms. The sine is an odd function that only has odd powers of the times t. But let's look at the cosine because it's nice and symmetric and easier perhaps to see. The cosine starts out with the 0th power, which is just its initial value of 1 at 0.
Dr. Harter, just one question.
Yeah.
We get these series expansions for cosine and sine function from Euler's identity, right? Like we define each the I theta as cos theta plus I sine
theta. Okay, you're jumping ahead of us because that is exactly what we're going to do.
Oh, okay. Oh, I thought that you got from that one.
Right. This is how you get that most easily, power series. Yes, that's what we're after here. But right now I just want to look at the real function. You know, see how it behaves. Okay.
So then, Dr. Harter, can you once again say how did you construct this series? Like for a real t, how did you construct this series for cosine and sine?
Well, we would have done the same thing that we did for the exponential.
Okay.
That is, I would take the derivatives of this in order to make the velocity, acceleration, jerk, inauguration, revolution, and so forth at time equals 0, and stuff them in, right? So that's where the Taylor series, actually it's called the Maclaurin series when you don't do it around some other point besides 0. Taylor series, I would make a series starting here and here. We'll talk about that.
Oh, okay. So
on.
basically, you're differentiating cosine. You're taking even derivatives of cosine, evaluating that at t equals 0, so you get 1 because cosine 0 is, and then it's like, okay.
Yeah. Same. It's really the same as, you know, going through this sequence. See? I mean, basically, we're deriving Taylor's or Maclaurin's formula, right? Does that make sense?
Yeah.
Okay. And this happens to be the result for the exponential, but that's the result for the cosine. And the sine is in some ways similar, but you see, you start here, and all you need is this. Then the quadratic part takes you to about there. See the parabola? That's the quadratic parabola of 1 minus t squared over 2. Is that guy right there. Okay? Now he peels off. I can see purple pixels coming out of the black pixels right about there. Okay, so I would say he's good to 1% or so up to that point. Okay? Then this guy takes over. That's a quartic fourth. That's the blue. Okay, there's a quartic function that's even. 1 minus t squared plus over 2 plus t to the 4th over 24. See, these are getting really big fast. Okay, so this is an interesting potential for quantum mechanics and classical mechanics, a 4th degree polynomial that has two wells that are nice and symmetric with respect to each other. And that function is good, and you can see the blue peeling off right about there. Okay? See what's happening here? Now my next stop is the 6th, which is drawn in blue right here. The 6th degree polynomial, really quite a sight. It's a little thing with a lump on it, and then it turns, and there it is, you see. So that's the 6th degree polynomial right here being plotted. And you can see it goes past where the blue is no good anymore and continues quite precision is good. And I don't see it popping out in here anywhere. And that's what's amazing about the power series for this particular functions. You see, it's only here that it says, oh, I don't want to play this game anymore. Goodbye, right? That's the 6th, you see. So when it breaks, just, I'm out of here.
So I'll just have one.
Same with the 8th.
I just have one question to have that. So if we just have the right hand side, like 1 minus t squared over 2 factorial plus t to the power 4 over 4 factorial plus 1 and so forth. Yeah, and if you plot all those things for a range of t, how do we at the end get cosine of t? Like all these things should add up to cosine of t, right? So we know how cosine of t looks like. And from in this graph, we see that when between minus 1.5 to plus 1.5 on the time axis, all these plots overlap for the very narrow interval of time from minus 1.5 to plus 1.
They overlap until their death. Each one of them has a place where it dies. Its accuracy dies. Its precision dies. Yeah. And it dies fiercely, right? The 10th, right? Comes peeling off here. The 8th. Peeling off there, the 6th peels off there. You see.
So from this plot, it's evident that when the time scale, when the range of t values is small, for smaller values of t, this
the increment that you need, that you gain by having another order.
Right. Yeah.
You see. Now, where this is a lesson is with regard to perturbation theory. Most of the things that come out of quantum mechanics are oscillatory. And to produce those things with power series, that what you get from perturbation theory is problematic, you see. If you go too far, it's completely wrong. But if you stick within certain realms, it's pretty good. Now, how does an actual calculator calculate cosine of t? They don't use this. This would not work. This would be impractical. They solve the differential equation for cosine t numerically using Runge-Kutta. That's what the circuit in your calculator actually does. And if you ask for a cosine on a computer, that's what's going to happen. A differential equation is going to be solved to give you that cosine.
So what is it? Okay. So
that's what's built into a computer.
So you solve the differential equation whose solution is cosine of t.
Yeah. Using the Runge-Kutta. Because Runge-Kutta is very stable. You see? And whether you use 4th order with adaptive step size or whatever, there are all kinds of different routines to make you have high precision for the cosine. And even the cheap calculators that you get for now I've seen one for $5.98 at Walgreens. Okay, that's what's going on inside the Walgreens calculator. It's an incredibly accurate solution by differential equations, not this series adding. That's way too full of error and too much calculation at high precision than you really needed to make that one work, as you can see. Now, it's not as... The question is, when's the peel off? If I were to do this plot using half a micron precision, so that I was looking at thousandths of each of these pixels here, I would see that the purple had deviated right here, and that the blue had deviated right here, and that the green had deviated right here. You see, deviation is already taking place right here for all of these. It's just that it's very small. Exponentially small, it turns out. That's what's really quite remarkable about these functions and then these polynomials. See. But what you do notice is, to a precision of 1 pixel, say here, okay, the distance between the next peel off is pretty much constant all the way out and forever. This curve, it's the difference between, say, 16th here and 18th right here is just about the same as the difference between a quadratic and a quartic. About that, right? If pixel precision is what you're seeking. So, this is, something I think you should see. And I've never seen anybody go ahead and plot this. The same thing's happening with the odds down here. You see. And in fact, that distance is the same. Hold your hand up like that, and it's about how big it is, right? All the way out for infinity, as far as we can tell. Now, it takes a lot of mathematics to prove that, but I would guess that if you did that, that's what it's going to give you. Okay? Now, what about imaginary interest? We have e to the rate times time, right? Let's make the rate imaginary. Now, what happens in a bank if you make the rate imaginary? Go to jail, right? But while you're doing it, not anymore.
Bankers
right?
never go to jail.
Nobody goes to jail if you're dealing over $1 billion, right?
Right.
If you're doing it for 100 or so, you go to jail for your lifetime, right? But if you're doing it with a hedge fund or something like that, right? You get a bonus. Okay? So, but anyway, you know what happens when you do. The accounts are going to oscillate. That's exactly what happens here. So, that silly little analogy can be taken. But the basic idea is that I'm going to look at the Taylor series with an I in front of that. So I'm making my phasor algebra right now. In each of these cases here, I take the i's first power as I, second power minus 1, third power minus I, fourth power plus 1. Then I start over again. At the fifth term, I have an I, and it goes every 4. But what's interesting is that they alternate between being imaginary and real, imaginary and real, imaginary and real. So I just simply separate the series that has the real terms, and there are even functions, the cosine, and then the other guys that have an I on them are giving us the sine function of theta. Okay, so we're just taking this result and getting this, which is a crown jewel of the mathematics of Euler and others that worked on this in the 1700s, early 1600s. Okay, so that's the graph of this thing that we use to make our usually clockwise motion phasors with a minus omega t in for the angle. And I'm not going to say too much more about that particular use of it. The phase analysis is interesting for its own right later on. Now, I'm going to just go through the utility of these things. What good are complex exponentials? Can't remember cosine A plus B or sine A plus B. Just factor e to the I A plus B. There it is. Okay? So, e to the I A plus B is cosine A plus B plus I sine A plus B. Let's just separate these two. There's e to the I A, cosine A plus I sine, e to the I B, cosine A so on, right? And put together the two that are real, that is cosine of A, cosine of B, and then sine A and sine B, that's also real, but with a minus sign. Great. That's going to be cosine A plus B, but you're also in the bargain getting sine A plus B in the same expression. The imaginary term, sine A cosine B and cosine A sine B, is the answer to that particular expansion. So it's this sort of thing that makes the phasors powerful because they can do this sort of trigonometric identity. This is just one of many trigonometric identities that you might want. Quick derivation of cosine law, same thing. Okay? So these are, I think, things that you probably are already vaguely familiar with. I just want to point them out and sort of list a few of the things that you get from this amazing piece of Euler, or de Moivre, I don't know if that's the correct pronunciation, construction of e to the I something. So here again is the thing that tracks position and velocity for our oscillators. And we'll come back to that in Unit 4 with a vengeance. These are what we call Cartesian forms. These are polar forms. These are things that you should already be quite familiar with. Cosine and sine, of course, being half sum and half differences with real and imaginary coefficients. Okay, now here's something that I think really needs to be said, although it's fairly obvious. We've talked about matrices that do rotations, that is written out in vector form, a thing like that. We can get that immediately from e to the I phi acting on a thing called z, which we'll call x plus iy, very common in study of complex variables to write z equal x plus iy. We're going to do it again several times before we're through here. E to the I phi is our Euler identity right here. And what we get, of course, is a real part, x cosine phi minus y sine phi. And then we get an imaginary part, which consists of this times this, plus this times that. So we get x sine phi plus y cosine phi, right? We'll just translate those into the real part, which will go with the x-axis, and the imaginary parts, which will go with the unit vector of the y-axis, or do it with a matrix. Basically, there's this term right here, after I've operated with this matrix, and there is that part right there. So that relationship is worth knowing and then thinking about. If I have something like this and I act on it with e to the I phi, if I have this z sitting right here, then it is going to rotate me counterclockwise if phi is positive. And this expansion is showing that right there. So treat the function of a complex variable, particularly exponential, as a rotator, finite rotator. All right. Now, some more vector analysis. This, you're going to teach mathematical things to physicists. It helps to do it this way because it shows different ways of looking at these things. It shows how they were derived originally, or probably. Take two complex numbers and make a product of them with a star in between. Now, what's star? The star is a symbol for what's called complex conjugation, where you simply take whatever it is you've got here and turn I to minus I. So I take the A star, that means I take the complex number AX plus IAY and change it to AX minus IAY. That's the only tricky thing here. Once you've done that, then you just multiply this thing out. and you get a real part, which is this times this, and then that times that is also real, in fact positive this time. So I get ax bx plus ay by, and then I get the imaginary part. The imaginary part is ax by minus ay bx, and you recognize this immediately as the, shall we say, third component of a cross product. And that little trick we'll be doing a little bit here. The imaginary part is a vector or cross product, but we're just taking a uppercase Z component normal to the XY plane in what we write here, you see. Now this is something we're going to generalize using the quaternions. There are 4 quaternions, one of them which gives a scalar product, and then there are 3 left to give us all 3 components of this. That's what we'll do in Unit 4 when we talk about the effect of the, shall we say, rotation of 2-dimensional oscillators.
So is this the same thing that we use quite often in quantum mechanics involving Pauling matrices, the sigma dot A dot times sigma?
That's what we're going to get. That's what we're going to get, when we do that. But I thought you ought to see this first so that you aren't so surprised by that result, and also remember that result better. Notice that if you write this in polar form, that is, if you write A star B as A e to the I theta A star, well, this is real, so nothing's going to happen with the star, but the star is going to change that to minus, so you get this thing. And then you have B e to the I theta B, that's what B is, it's not starred. So it's just sitting there. And then we put those guys together as e to the I theta B minus theta A. Okay? So you get the real part of that is e to the I of this e to the I A theta minus theta B is the cosine of theta B times that product is real, absolute values, and sine. Okay, so that's another way to look at this, you see. As a magnitude times a sine and another magnitude times a cosine in the first term. Okay? So you see this is a case where mathematical discoveries are reinforcing each other in a, I think, fairly coherent and pleasing way. So one of the things to do is go ahead and write the Cartesian function back, just to get back to this point and check it. Okay? So far we're at stage 5 of answering what good are complex exponentials. What we'd like to do is do some calculus. So I call easy 2D vector calculus, in particular vector derivatives, will be part of this story. So here is where we show that if you take a derivative with respect to a variable like z, which is x plus iy, you just use that notation, you will get 2 things. Just as we got 2 things by doing the product of complex numbers with a star, in this case, what we're going to get is a divergence and a curl. Just like we got a scalar product and a cross product, sort of a weird cross product that only has one number because we're only interested in the 2-dimensional description here. But what I'm doing is I'm making sure that we got our ducks in line, as we have a thing called z, which is x plus iy. We have a thing called z star, which is x minus iy. These are 2 independent variables, just as independent as the x and the y, which are respectively the half sum and half difference with an extra I in the denominator, that is minus I times z minus z star all over 2. Okay? So what we're going to do is apply the chain rule here. I'm going to say, okay, I'm going to define a total derivative, that is a derivative of this function with respect to z, as, I'm going to use the independent variables x in the chain. So I'm going to write this partial x over partial x of the partial of f with respect to z. And then partial y over partial y of partial f with respect to z. Okay? Well, partial x with respect to z, that's this thing, is just 1/2 z. Okay? So that's what we're going to get for this. We just have 1/2, and then I've got a partial x with respect to z, that's this thing right here, okay? And I take a partial x with respect to 0, I just get 1/2. Okay, that's what those two connect up. And then I look at y, okay? Well, I'm going to be looking here at the partial derivative of this with respect to z. That's partial y with respect to z right there. I'm going to be looking at only this one. That's an independent variable, which is giving us 0, just like this one did. So I'm going to get 1 over 2i, or minus I over 2. So this is an important thing that we're going to use over and over again. The operator d dz is equal to 1/2 of a partial with respect to x minus I 1/2 partial with respect to y. Now, this had better be, if the function is real, this had better be the conjugate of this, and indeed it is. The derivative with respect to z star is simply this thing with a sign reversal, which makes a plus sign. But that 1/2 is very important. We're going to see what that does to our physics of divergence and curl as we go through this. So here's the deal. The derivative chain rule, okay, where d dz is this, okay? We're going to do the d dz of fx plus I fy. That's a function. Okay, and here's the derivative that's coming from this thing right here. All right? So we're going to multiply through, we get 4 terms here. Very similar to when we multiplied a star b as vector. Now it's an operator in a function, a complex function. And it will eventually be called analytic function if it obeys certain rules. Okay, so here is this thing right here is the real part. Remember, there's a half on all of this. Partial x with respect to fx, and then a minus I times a plus I is 1 partial y with respect to fy. So here is the scalar product of the operator. This is a scalar product of a del and an f in 2 dimensions. Then I get the imaginary part, which would be this times this I right here, pull the I out, I've got the 1/2 still, okay? Partial fy with respect to x, fy x, gives me that term, and then this one right here goes with that, now has a minus partial fx with respect to y. That's the curl, but only the uppercase z component of it, that component that is perpendicular, normal to the variables that we're working with, which are x and y.
So why do you put a modulus sign? Why are we taking the absolute value?
Well, I'm going to drop all of this stuff some of the time, but what I'm warning you is that if we were doing quaternions, I'd have 2 more terms here, because it is a 3 vector, right?
Oh, yeah.
And I'm only interested in the last term, component, the component that's normal, you see, to what's going on in the xy plane. So this uppercase z is whatever's sticking out of the screen here.
Oh no, in this case I was asking, why do you take the absolute value of curl of f? Like,
well, simply to indicate that I only want the magnitude. You see, this component magnitude, right? That's the way you often write vector things, right? Is you put a little subscript here and say, what component of that vector do you want, right?
I have one more question. If your f had been a 3-dimensional function, f was a function of x, y, and z,
well,
then how do we write?
There you're asking the question of how do I get the quaternions to work for that?
Yeah, like, because z is x plus I,
yeah.
y, so...
There are many situations where you can pull that off, and there are many where you can't.
I also have one very general question which I've been having for a while. When we talk about derivatives, we talk about first derivative, second derivative, third derivative, so on and so forth.
Say that again.
Like when you differentiate a function, we talk about first derivative, second derivative, so on and so forth, dy by dx, d squared by dx squared, so on and so forth.
And we talk about partial when we have multi-values.
Is that something called a fractional derivative in mathematics?
Oh, I worried about that when I was first learning calculus. And yes, there is. There's a half derivative. That was one of the things that Feynman, when I interviewed to get a job, first of all, he said, well, what have you done? I said, I read your book. And he said, I don't give a shit what you read. I want to know what you've done. And I said, well, I made this funny analog Fayetteville differential. Oh, he just loved that because he liked gadgets. And then the thing that really probably got me the assistantship was the fact that I'd worked on a half derivative and figured out ways to calculate a half derivative. So that when I did two of them, I got a whole derivative, and I could even do correct. He said, yeah, I used that once. He used it to solve a throw and outflow in such a weird way that it was completely rejected by the referee. But it was a much more elegant way to do some solutions to diffusions equations. So.
Because the way we define derivative in analysis is df by dx is limit delta x tending to 0, f of x plus delta x minus f of x by delta.
Yeah, that definition doesn't work so well. So the real answer, I mean, it seemed like both of us were missing the real answer is you do the whole thing in Fourier transform space, where dd x becomes k.
Okay.
Then you want to power that, you just take k squared and then you transform back. But what I was using was what's called the Bromwich integral, or some weird thing, which is just a sort of a funny way to do Fourier transforms. Anyway, fun and games with mathematics for physicists that aren't mathematicians. Right? That's the first thing a mathematician worries about. It's good. Is how do you take fractionals? Anything. All right, section 7. We've got about 10 minutes here, so we can probably get through this. And this is where the geometry really comes in. What we're going to do with this thing is, and this is really good. What you can do is invent source-free 2D vector fields for which they have no divergence. That means there's no scalar source, and no curl. That means there's no torquing or circulation in the field. Okay? And the way you do that is you say, we can invent a source-free 2D vector field that are both zero divergence and zero curl. Take any function of z, your favorite function, sine z, e to the z, z squared. We're just going to do actually f of z equals z first. It's already interesting. Okay? Conjugate it, let's change all the i's to minus I, to give f star z star. Okay? Usually you don't need to put a star in the f unless you've already got a function that's got imaginary parts to it. I'm saying take a real function, then you don't have to have that star, but you do have to have this. And the idea is that df star with respect to z is identically 0. And you see the dz here is consisting of a term of divergence and curl. So if this comes out 0, that means both of these are 0 in the field. Okay, the field that's result. Now, in the next screen over there, we're going to look at an example, namely this one. Let's take f of z equals z. A is equal to this little number here to be complex. That's interesting too, to make that complex, but we won't do that. We'll just do the simplest thing here, where it's just plain old z. I'm keeping the a here just for the fun of it, but here's the basic idea. it's telling me that if I take a divergence of the vector field that I get from this, now you see what it was, is I took z star. You see, I replaced the z with z star. That means I replaced the z with this thing, x minus iy. And the idea is, check very quickly that I don't have any divergence or curl or such a thing. Partial of x, fx, that would be this part right here, a times x, okay? That's this guy right here with respect to x. A plus partial respect to y of the other part, which is a y with a minus sign. Now that certainly comes out to 0, okay? A minus a. And then the curl does the same thing. Only this one, both terms are 0. This is partial of respect to x of y, that's 0. Partial of y with respect to x, that's 0. So that's 0 minus 0. That's even zeroer than this one. Okay? But the idea is that we make what is called in hydrodynamics things like a divergence-free laminar field, DFL. All of these fields that we're going to get are DFL. It's not quite like DOA, which is dead on arrival, but these are, in a certain sense, dead, that they have no sources of any kind, divergent or curling. Okay? And this is our first example right here. Okay, so just to review, invent source field vector fields, just pick any function you can think of z, conjugate it, and then build a field out of it using the z star that you got from conjugation. And you will automatically have everywhere, no divergence, that is, no sources in the neighborhood. Now there's got to be a source somewhere way up north here. There's got to be a sink, say negative charge if we're talking about electric fields, but if we're talking about hydrodynamics, there would be a drain over here, a source up here, and a source down here, and a drain down here. Okay? Now you say, hey, those kind of look like they're diverging, and maybe even they're curling. It seems to me that you've got more shear on this side than you do on this side. We're going to show that's, physically we're going to show that's definitely not the case. But anyway, that's a typical field. Now what's the difference between, in this case, the field that you get with AZ and this one we're getting with AZ star? What's the difference? Only difference is the y component has been negated. Every one of these vectors, if I just done z, would be pointing up. Let's take a good big one here. This vector right here, which now has a negative y, would have a positive y, so it would point up. It would actually point away from the center here. So what I would be producing would be a bunch of vectors that really had a divergence. Big one. I wouldn't have a curl for the reasons we already said there, but there would be a big fat divergence if I had simply done the z. Okay? So that, I think, is one nice example of this. Now, we've got a few minutes here to talk about the sort of potential that goes with one of these things. And that's what's really cool here, is a complex potential that is a potential that contains both the scalar and the vector potentials. Okay? So any DFL, divergence-free laminar field, is a gradient of a scalar potential. Or, and that's what's cool about these fields, is it can also be expressed as a curl of a vector potential. It's one or the other or both, any combination of both. That's what's not, I think, realized by physicists to teach this subject. So I take a complex potential, okay? This will exist such that its z derivative is d phi dz. this field. So really all I have to do is integrate that equation to get the potential. And that's a nice, powerful thing about this whole method. But the complex conjugate of this thing has a z-star derivative like that, giving that field that we want. That is, this is the field that we're after. So you need to have a minus sign right at that point. So let's take a look at this. To find the phi, you integrate f of c. That will give you a phi, and then you can easily make it into f, phi star. You isolate the real part, that will be the scalar potential, the imaginary part will be the vector. So here's f of z equal d phi to z implies phi equal this plus this is the integral of f dz. Now the f that we took was a times z, so we're going to get 1/2 az squared by doing that integral, pretending that the z is a variable that we can integrate just like a real variable. That's a little bit dicey right there, but it works wonderfully. So here is the potential phi. Consists of a real part, okay? Take the real part of this thing here, it consists of all of this, but there's the real part, there's the imaginary part, which will be that guy right there. And I'm going to switch over to this screen where I've got this field sitting there. So what I do is I pick, whatever field I want here. This would be f of z equal constant. That is pretty simple. F of z equal constant is pretty trivial. But f of z equals z is not. So let's go back and take that one on the menu here. Unfortunately, this is a app that is not yet a web app. It should be fairly simple, but I apologize for not keeping up this. This is a good old Macintosh app. So let's draw the vector field. There it is, okay? And then what I'm going to do is I'm going to just click somewhere and make a potential. That's really easy to do numerically. Everywhere I click, I'm making the potential, scalar potential, equal a constant. Those are the red lines. Red for hot, I guess, if you wanted to think about a voltage. This would be if this was an electric field. Okay? So there is that. Now this will remember those curves if I go back to main control here. And instead of plotting the scalar phi lines, I plot the vector lines. I can plot both too, but I'd rather do that just to keep things in order here. So now I can go and what do I plot? What does the vector potential really mean? It's called the streaming potential. You see what it's doing there? And I'm thinking of hydrodynamics as water flow, so the blue here is indicating where the water's headed, or any liquid that's incompressible will follow very closely these lines for this particular function. Which remember is a source coming from high above the screen, you see. And if I can get it right on there, you see, you can get real close to this thing, but I can never quite get it, right on. Same thing for the source below. Okay? And the equations for these curves we've already calculated. The red one, the scalar potential, is this, x squared minus y squared. Equilateral hyperbolas that cross the axes, the red curves that you see on that diagram there. And then the other one was just simply a, x, y, the blue curves. They're equilateral hyperbolas who use the asymptote the axes as asymptote. The scalar potential uses the 45-degree lines as asymptotes. As you can see, there's a 45-degree line going right here, or right there, all the way down through here, the next those. Okay. Now the other way to plot these, which I'll do just a minute here, but the point of this figure right here, which shows the field and the potential, and that's several figures for examples. All of this stuff is in Unit 1, Chapter 10. This happens to be Figure 10.7 that we've just created parts of right here. The idea is that this potential is telling us what any integral, force integral, if this were an electric field, the integral of the electric field dot dr, is not dependent on a path, and it's simply the difference between the voltage here and the voltage there, which you read off from each of these curves. Now, going back and looking at the thing that we've computed on the screen here, at any point that I put this cursor, you see, equipotential is right there, and the phi potential for that is minus 0.66, and it's getting more and more minus as I go this way. Here it's already up to minus 1 volts, and then minus 2.5 volts. You see, so I'm going uphill here. Now you notice that the arrows are pointing uphill. This is clearly a mathematician's definition of potential. Remember, I warned you about that. Okay? And so I do not have a minus sign in here that a physicist would require. But I don't want minus signs right now. That confuses the mathematics and makes the algebra a little harder. So that's why we're using what is historically a mathematician's definition of force and potential. Okay, let's see if there are a couple more things I can say about this. And this is really important for our mechanics course, because we're going into the study of generalized curvilinear coordinates. And this is the bonus of this method, is that once you've defined this f of z and its integral, which is the just plain calculus one-dimensional integral of that function, you get a free coordinate system that's curvilinear. Now I put a star on this just to indicate it. Actually it's OCC, because every one of these has to be orthogonal. We'll see why that is. That's a very special property of this particular way of getting curvilinear coordinates. So at this point, I think it's probably a good idea to pause, and we'll go on next time into really looking at the mechanics of this relationship between potentials, fields, and a coordinate system. You can see this is a coordinate system with nice right angles between the streamlines, which are the gradients of the potentials and the actual potential curves. So I will stop now, just about the right timing for the class itself.